If you buy a typical commercial smart hub, you are trusting a system that relies entirely on an active internet connection and corporate cloud servers. When your network drops, that expensive hardware turns into a plastic brick. You can't even turn on your living room lights. But there is a way to build a system that never goes offline. It starts by pulling a 2013 Motorola smartphone with exactly 1 GB of RAM out of the recycling bin. To make this work, we have to wipe the Android operating system completely, flash a bare metal Alpine Linux base, and compile a localized large language model, or LLM, directly on the device. True technological sovereignty comes from reclaiming forgotten legacy hardware, not paying a subscription fee for access to a corporate walled garden. Our first step is fitting an AI brain into this severely constrained device. We use a C-based inference engine called llama.cpp to load a 300 million parameter model into a strict 400 megabyte memory footprint. To manage that brain, we use ZeroClaw, a Rust-based autonomous agent framework designed by university researchers for a tiny 5 megabyte hardware envelope. But if you try to install a standard ARM binary directly onto the phone, it will instantly crash. Alpine Linux uses the Muscle C library, which is incompatible with standard compiled software. To bypass this, we use a separate desktop PC to cross-compile the agent. Cross-compiling lets us build code on a powerful machine while explicitly targeting the phone's ARM v7-unknown-linux-muscle ebhf architecture. Once compiled, we push that finalized 5 megabyte binary over a direct USB tether, bypassing the phone's compilation limits entirely. Mastering cross-compilation proves that artificial software limitations on legacy hardware are tooling mismatches, not physical barriers. Next, we set up the execution layer. We deploy PM2, a process manager that keeps background services running automatically, to handle our node-read logic and a local DNS broadcaster. Almost immediately, PM2 throws an address in use error that completely blocks access to port 53, a critical lane for network routing. The culprit hoarding the network port is a background OS service named systemd-resolved, operating like a digital squatter. We clear it out by executing a series of terminal commands to permanently disable both the service and its hidden trapdoor sockets. Seizing absolute manual control over default OS network ports is the required first step in establishing a truly private network environment. This brings us to the next adversary in the network chain, the ISP-provided Optimum router. As seen in this interface, the router strictly prohibits broadcasting custom local domains like moto.old. Relying on consumer-grade ISP hardware creates an inescapable dead end for self-hosted domain routing. Our bycast strategy abandons the physical router entirely and hard-codes the translation rules directly into the desktop operating systems on the network. By editing the local hosts files on our Windows and Arch Linux rigs to point directly to the phone's IP address, we instantly circumvent the corporate hardware lock. Network hardware leased from corporations is designed to restrict user autonomy. Taking back that control requires overriding DNS at the root OS level. We also want to turn the phone's physical glass into a persistent visual dashboard using the FBI Image Viewer utility. We hit a visual glitch here. The custom dashboard image loads successfully, but it is instantly overwritten by a black screen. Checking the logs reveals a hidden operating system conflict. The default Linux login prompt, ageti, is waking up late and hijacking the TTY1 display interface. Achieving a dedicated kiosk mode on bare metal Linux requires systematically disabling these default OS login prompts so your application can hold the screen. Everything we have built funnels down to one final payload, a single bash script named light_control.sh that acts as the universal translator for 3 completely distinct lighting APIs. API stands for Application Programming Interface, which is how different software programs communicate with each other. First, the script injects raw hex codes directly into the device path to command a Bluetooth bulb. At the same time, it transmits a JSON payload to the Philips Hue API. Finally, it shoots a post request to a WLED microcontroller. One shell script allows these 3 incompatible hardware ecosystems to function as a single unified unit. Now let's trace the completed execution loop. A user sends a Telegram text message, which is securely intercepted by the local ZeroClaw agent. The agent hands off the text to the 300 million parameter LLM, which processes the request, makes an autonomous decision, and hits the node-read endpoint to trigger the master bash script. Instantly, the isolated room alters its environment based purely on the offline AI's decision. We now have a fully autonomous, offline smart home intelligence running entirely on a discarded device with just 1 GB of RAM. Ownership of your smart home is achieved by stripping away the software limitations placed on the hardware you already own.